Okay, we're going to talk about curved mirrors now, 17.2. Shout out, I guess, to Ellen, who did such a great job in the play. So good job, Ellen. Anyways, so we're going to look at curved mirrors. We're going to break this up into convex and concave mirrors. The way I remember it is concave are the caved in, so those are the ones that are curved inwards. Convex are the ones that are bulging out. But we could also create real or virtual images, and we're going to distinguish between what's a real image and what's a virtual image, as well as what the object is. So we're going to look at this idea of spherical concave mirrors, and we're going to do some ray diagrams, and then we're going to look at convex mirrors, and then we're going to look at some calculations and how to do a little bit of math with this stuff. Again, to start with, if just look at a spoon, shiny spoon, you'll notice your reflection looks different than a plane mirror. If you look at the um, inside, it curves inwards. If you turn it over, it's going to curve outwards. The property of the curved mirror and the images depend on the shape of the mirror and as well as your position, how close you're holding it to your face if you're doing the mirror thing. So if you hold the inside of a shiny mirror, excuse me, a shiny spoon, the side that holds the food, we're going to call that a concave mirror. Again, caved in. Um, the concave mirror has a reflective surface, the edges of the curve towards the observer, and so the properties of the concave mirror depends on how much it is curved. So we're going to start looking at this idea of a concave part. So this would be like the inside of a spoon. But what we're going to do is we're going to do a spherical concave mirror. In other words, if this were to continue all the way around, this would be a perfect sphere. So we're looking at a part of a sphere that we've cut out in the shape of a mirror. So again, this is a cross section. If you're looking at it straight on, it might be round. Um, we want to look at some of these different parts, what the C means, R, F. So we're going to talk about all these different little parts of the mirror. The spherical mirror, the mirror is shaped as if the section of a hollow sphere, and it's the inner surface of that hollow sphere. As far as some of the geometry, C would be the center of that sphere. Okay, therefore R is the radius, and so we're going to refer to that as the radius of our mirror. Um, we're going to have a section that runs right down through the middle. This would be like the diameter of the sphere. Um, so if we go from the center of the sphere to the edge and right out through the side, we're going to call that the principal axis. Think of this as the middle point, the midline. And it's going to hit our mirror right in the middle of that section that we've cut out. M is the center of the mirror then. When you point the principal axis of a concave mirror towards the sun, all the rays are reflected towards a single point. You can locate this point if you move a piece of paper towards or away from the mirror. Again, you have to have a really large mirror, smaller piece of paper. You could figure out exactly where the focal point is. This spot, this focal point is a point where all the light rays will be basically converged by the mirror into a single point. So we think about all the sun's rays coming. Essentially, by the time they get here, they're pretty much parallel with each other. When the rays strike the mirror, reflected in accordance with the law of reflection, the figure shows that the rays parallel to the principal axis, so a ray coming in from the principal axis hits the mirror, bounces off. Remember angle theta, or theta I and theta R. It's going to bounce off at some angle. Another ray coming in here would bounce off. Because the curve's not so great here, it would bounce off at a lesser angle. It would turn out that all of these rays would basically go back through a particular point, F. We're going to call F the focal point. Turns out that F is, for a spherical mirror, is halfway between the midpoint of the mirror and that point C that we talked about before. So we say that the focal length then is going to be 1/2 of the radius of the curved part of the mirror. So focal length is positive for a concave mirror because it is a point of converging lines. In other words, all the points come together at a certain point, and that is a positive focal length. You already draw rays for a regular mirror. We're going to find that this is even more useful if you're trying to deal with curved mirrors. You almost have to do the diagrams. Not only can you locate the image this way, but you're also going to be able to tell what the orientation is, whether it's up or down, also whether the relative size, whether it's bigger or smaller. So let's take a look at this.
You can use a ray diagram to determine properties of an image formed by a curved mirror. The animation above shows the formation of a real image, an image that is formed by the converging of light rays. The image is inverted and larger than the object. The rays actually converge at the point where the image is located. The point of intersection I of the two reflected rays determines the position of the image. You can see the image floating in space if you place your eye so that the rays that form the image fall on your eye, as in the animation above. As the animation above shows, however, your eye must be oriented so as to see the rays coming from the image location. You cannot look at the image from behind. If you were to place a movie screen at this point, the image would appear on the screen, as shown above. You cannot do this with virtual images. To more easily understand how ray tracing works with curved mirrors, you can use simple one-dimensional objects, such as the arrow shown above. A concave mirror produces an inverted real image if the object position, DO, is greater than twice the focal length, F. The object is then beyond the center of curvature, C. If the object is placed between the center of curvature and the focal point F, as shown above, the image is again real and inverted. However, the size of the image is now greater than the size of the object.
Okay, so again, if we do our ray diagrams, we'll be able to tell whether we have an inverted image or whether it's greater or smaller. Okay, so again, we're going to try to do a little ray tracing here. So you can use a simple one-dimensional object like an arrow. We put a little point on it so we could see which direction the arrow is pointing. That way we could tell whether our image is actually inverted or right side up. We're just going to focus on a couple of rays. Remember, there's going to be a million rays coming off of this point in all different directions, but we're going to focus on one ray that comes straight out parallel with this line down here, okay, and see what happens to that ray. And then we're going to look at a ray that passes through the focal point. And what happens with that ray, what you'll notice is after it hits the mirror, it's going to bounce off and it's going to come back out straight. Okay, so that's just kind of one of the things that we're going to notice about our rays here. Concave mirror produces an image, an inverted real image. It's a real image because it's an image on the same side as the mirror is, and you could actually put it on a piece of paper. Remember, a flat mirror creates virtual images on the other side of the mirror. You can't put a piece of paper and see that image, but you could put a screen or paper here and actually see the real image that's projected. Again, it's an image. It's not the object, but it is real in the fact that you can actually project it on a piece of paper. It's real if it's on the same side as the mirror as you are. The object is then beyond the center point of the curvature, C. Remember, that would be the center of our circle if this was an entire circle. The object is out here. If the object is placed between C and F, in other words, closer than the center of the circle but still outside the focal length, okay, what's going to happen is you're still going to, if the object is pointing down, it's going to invert and point up, but it's now going to be larger than the original image. Okay. One of the ways that they use concave mirrors is if they came up with a concave mirror like this and then they punched a small hole in it, not enough to affect all the focusing, but just so you could see through it, and you put another mirror out here. Again, this mirror is smaller than the tube, so that light could come around it and still hit to the mirror. So the light's going to hit the mirror, bounce off of there, bounce back. And what we've just done is we've taken the mirror right side up here, upside down here, back to right side up here. So you're actually looking at the image right side up. 1663, a Scottish astronomer came up with this idea. Again, it's composed of a large concave mirror, this one back here, and a small concave mirror up here, arranged so that the smaller mirror is outside the focal length of the larger mirror. Parallel rays from a distant object, this parallel ray, strike the mirror, reflected back towards the smaller mirror. The rays are then reflected off the smaller mirror, coming back in the other direction, and it forms a real image that is oriented like the object. If we try to do a little bit of ray tracing, one of the things we find, however, is that this would be basically what the ray tracing would look like. You'll notice that the ones that are hitting closer to the axis are basically going through the center, the focal point. However, some of the other ones are not. The ones that are further out, again, if they were reflected, they're not going to reflect necessarily through the axis. So the rays are reflecting off the mirror. Again, only the ones that are parallel to the para-axial rays, which basically are close to the principal axis, are called para-axial rays, are reflected through the focal point. The other ones go someplace else. The image formed by the parallel rays reflecting off the spherical mirror with a large diameter and a small curvature then are basically going to form a disk and not exactly a point. We call this spherical aberration, and it's going to result in a fuzzy, not sharp image. If we wanted a perfect image to form, we would have to use a parabola instead of a sphere, and then we'd get rid of the spherical aberration. These are very, very expensive, though, to do, so it's a lot cheaper to make a spherical mirror. Those are easy to make, and then use some secondary mirrors or lenses and correct for the image. So we would take instead of the parabola, we would take a spherical mirror, and then we would correct. So the lower cost, less precise applications, we're going to use the spherical mirror and we're going to correct the image. Okay, if you have an object that approaches a focal point of a concave mirror, the image moves further away from the mirror. If the object is at the focal point, all the rays are parallel. They never meet. Therefore, the image is said to be at infinity. So the object could never be seen. What happens if the object is moved even closer to the mirror? Okay, so if you get in front of the focal point, what do you see? You're actually going to see an image that forms on the opposite side of the mirror, and it's going to be larger. So it's basically, if a makeup mirror does this, you could hold it real close to your face, and it magnifies whatever you're looking at. And since the image is behind the mirror, we say that this image is a virtual image. There's no way you could actually put that on a piece of paper. So the virtual image forms way back here, and again, it's similar to what we had for the concave, for the regular mirror. We have a ray that's going up here, bouncing off. Again, if the ray's coming out this way, we could basically backtrack it, and it's going to go through a particular point in space. Again, we take this ray, bounces off the mirror at this angle. Again, if we back shoot it or back trace it, it's going to go to here. Basically, where they all meet, where all these rays meet at, that's going to be where the image is formed at. So the two rays are located of the image at they can locate a point on the object. And again, ray 1 is drawn parallel to the principal axis. So we got ray 1 is drawn principal axis. It's going to go through the focal point. Okay. Ray 2 up here is drawn on the object, and it's going to go along a line defined as a focal point from the focal point up, and it actually goes out parallel to the axis. So ray 2, and then ends up again. If you think about it, going through the focal point back up, then it's going parallel. So ray 1 and ray 2 then, if we back shoot them, they converge and create a virtual image behind the mirror. And again, you can kind of see that happening here. We have a round mirror. The objects that are closer to the focal point are going to show right side up, but objects that are away from the focal point are going to be upside down. The flag is upside down, and this bench here is upside down. Magnification gives a position, gives a positive magnification greater than 1. That means that the image is right side up compared to the object. The inner surface of that shiny spoon acts as a concave mirror, and then we could change it into a convex mirror. But we're going to stop here, and we're going to cover convex mirrors the next time. So, okay, that's it, and we'll see if I do a quiz or not. Probably not have a quiz on this one. We'll probably have a quiz over the whole thing.